Okay, welcome you guys. This will be a short session. I will try to um, will actually solve this problem that I think can be solved easily in different way. So that what I will try to do. And in that solution in the last week, I forgot to consider that three-phase calculation, so that I will make the correction. So this is, um, I apologize for that mistake in the first hand. So we will try to sort it out here today. So this was the problem. Then this is a three-phase transformer of rated value of 330 MVA, and the primary side voltage is 34.5 kV, and the secondary side voltage is 138 kV, and they are star and delta connected. That means primary side is connected in star and the secondary side is connected in delta. And what we need to do, we need to draw the suitable diagram. That means CT connection, the primary transformer coil connection, as well the secondary coil connection, and also the CT connection. So appropriate CT connection and their ratio has to be determined. Let us just start doing this. We'll go back to my tablet and then try to sort it out. And try to bring a new one because I have already done one. So we will try to create a new note and we'll solve it from the very beginning. So hopefully this is recording, is continue recording. So let us just share this screen and then open my notepad. So we'll start from the beginning, and let me just share the problem, bring the problem so that I can write down the value. So take the black. So S is given equal to 30 MVA. Primary side voltage is given equal to 34.5 kV. And secondary side voltage is given equal to 138 kV, and they are star delta connection. So let us start drawing this diagram, simplify this diagram. And so primary side is connected in star. So I will try to draw this connection. And try to make it better. And they are star connected. So we'll make it a star connection, and then secondary side will make a delta connection. So I will connect it here, they will connect it here, and back and forth, and this is delta connected. Now this one we can just make the dotted line of the transformer. So this part is my transformer, and this is Y connected, and this is delta connected. Now we'll take a different color and try to draw this CT. So CT, Here also on the primary side, there will be CT. And now this one is delta connected, star connected. So that means this one has to be delta connected. So I'm just extending this terminal to be connected with the differential protection. And then I will connect in delta. And this one will be back to here. And this one is delta connected. So this is the star connection. So, sorry, this one is delta connection. So this one is delta connection. So star with star, this city is delta and this is delta. This should be star. So that means one of the terminal will be shorted to the ground. And then I will have the other terminal that has to be extended through this restraint coil. And I can connect the operational coil and make it ground. Let us do it in this way. And similarly, I will do the other coils, other branch, other phase. For other lines. So we will connect it here. And the third one is this one. And that will be connected with this one. This is connected the earth. So this is the restraint coil we can name. This is the restraint coil and this is the operating coil. So operating coil. And now we can identify the currents. Let us take different color. So this is, let us start with this one. So this is my primary side. So the one indicates this is the primary side and this P indicates the primary current of the city. So this current is flowing through this one, that is the primary current of the city. So similarly, I can write I2 and this is P. Now this is the primary current. Now the city secondary current will be produced by I2S prime, and this is flowing through this one this way, 1 2s prime. So same current should flow through the primary side, and this one will be renamed as I1s prime. But here it can be different than this current because this current is the line current here for this delta connection, and this one here would be equal to I1SP. So that's what we have missed in the last problem. So that can be easily explained through this relationship. Okay, so that means the line current is in the differential protection relay. In the coil, this line current will flow, but coil itself will produce the phase current. So I can write this one IPH. So this current is I1S PH. So this relation I can write down, or I think all of you know with the star delta relation. So then also I just try to draw this one here, and so that everybody else can understand this one. So this is the three line that is connected, and this is where I will have I1S prime. And the coil itself in the secondary will produce I1S PH. Now the turn ratio of the CT coil has to be determined for this phase current, and they are related with I1S prime should be equal to √3 I1S pH. So this is the relation we need to remember. Okay, so let us now go to the calculation of the real problem, and that is, we can just make the primary current calculation. So I need to calculate the primary current. I need to calculate the secondary side, transformer side primary current, CT primary current. And this can be calculated with a simple formula, that is S is equal to root 3 BL IL. And from here, I can find out IL is equal to S divided by root 3 VL. So I1P would be equal to 30 kilovolt ampere divided by root 3 times 34.5 kV, and that will give us 502.044 ampere. Similarly, I can calculate here the 30,000 divided by root 3 times 138 kV. And this is kVA, and that will give us 125.51 ampere. Now, as this one is smaller, we will start our turn ratio calculation with this one, and I want to convert this one to 5 volt, and the nearest value that we can get would be turn ratio of 5 divided by 150. And using this turn ratio, I can find out what would be the current in the secondary of the CT. So that can be calculated 5 by 150 times 125.51. And that will give us 4.167 ampere. Now, as per the differential protection relationship, this one has to be equal to this one. So I can write down from this relationship that I1S prime should be equal to I2S prime. And going back to this relation, that this current has to be the line current for this delta connected CT. So I need to find out I1S P in order to find out the turn ratio of this coil. So that can be given by I1S prime divided by root 3. And that will be equal to 2. So that will be equal to 2.46, I think. Yeah, 2.406. Okay, so this is actually coming from this one. So this I1S is nothing but I2S prime divided by root 3, and that will be equal to 4.167 divided by root 3, and that will be equal to 2.406 ampere. Now, using this current, we can find out the turn ratio, and that will be given by I1 S pH. That's what I have written, I think. Yeah. So that would be pH equal to N1, this is primary ratio, times the primary current, that is equal to 502.044. So from here, I can find out N1 is equal to 2.406 divided by 502.044. That will be 0.0048, and that can be written as 5 divided by x should be equal to 0.0048, and we can find out the ratio here. X is equal to 1041.67, and that is unrealistic one, because if I go to our table, we will find out that this one is not in the standard value. So we have to find out the nearest standard value, and this is 1000 to 5, that is the standard, and the next standard is 1000 to 1200 is to 5. So that means, okay, let me just share this one. I think I have not shared this one. So from here you can see that 1000 is to 5, that is the standard value, and the nearest one is 1200 is to 5. So this one. Okay, so that means we have 1041 that is higher than 1000. So we have to go to the next one. So let us just stop this sharing this table, and then we'll share the screen again. And we'll go back to our problem. So that means we cannot take this value from the standard table. We need to take the nearest value, that is equal to 1200. And now the problem is, so this is the solution of this problem. We have done the connection diagram, and we have determined both the primary and the secondary turn ratio. So primary turn ratio is 5 by 1200, and the secondary we have already determined 5 by so secondary is 150. So this is the required solution. But now, as you can see, that this turn ratio is expected in order to have the balanced current in normal situation. This expected to have 1041, but we end up taking the standard value of 1200. So that means this will not produce the required current of this one. So as a result, my I1S will not be also this one. So that means I need to have the characteristics, I have to determine the ratio of the restraint coil so that the slope of the characteristic curve can be changed. And that we need to find out what would be the what would be the slope of the characteristic curve, so that this mismatch can be nullified. And in order to do that, I need to first find out what is the actual current in phase due to this turn ratio. So 5 divided by 1200 times 502.044 ampere would be the current for this new turn ratio, and that will be equal to 2. Let me just take a look of the calculation. So this will be 2.092 ampere, and this will result I1S prime in the differential coil √3 times 2.092 ampere, and this will give us 3.62, whereas my I2S prime is 4.167. Now from here we can find out the relation from the relation of the characteristic curve ID equal to K into IR. So where ID is the difference between I1s and I2s, and IR is the average value, I1s prime plus I2s prime divided by 2. So we can do the calculation from here and write down K equal to ID divided by IR. So that will give us 0.14. So in order to nullify the mismatch, we have to have the slope of the characteristic curve of the differential protection is 0.14. That has to be done with the ratio of the restraint coil. Okay, now I think it's clear, and I will try to create another video on this, on the representation of the transmission line to the impedance line diagram, from the single line diagram to impedance diagram, and the conversion of the per unit, how to calculate the impedance, per unit impedance for that impedance diagram. And that will be useful for our next class whenever we do the calculation of the fault current. Okay, so yeah, so that is it for today. And I will